All right, welcome on in, everybody. Oops. Welcome on in, everybody. It looks like we are going to get today's session taught. I know I warned you last time that there may be a power outage at my house. It looks like the power outage is now not expected to start until 9 o'clock. So that means that I should be able to finish today's course because 8:50 when our class ends is, of course, before 9 when the power is supposed to go out. However, if the power goes out at some point or you just lose the stream, likely I lost power and it won't be coming back anytime soon, right? So not till, supposed to be out till 4, although sometimes they end early. So that's where we're at. Unfortunately, I've been thrown a bit of a curveball. The website I've been using for the visuals to show you things has been taken down, probably for a copyright violation. And I have not this morning been able to find an alternate. So basically, my slides or visuals that I was going to show you in order to help explain what's going on with the chapter has been taken down. So I'm a little bit disorganized here slightly. A little bit. So I'll talk about where we're going with the class. Things are moving fast, right? I mean, it's just going to move really, really quick between now. It's going to seem like, right now it seems like, well, we got plenty of time. The finals are like a month away. It's going to seem like it happens tomorrow because between the holidays and you're all going to be writing essays and for your English classes and finishing up your lab books for your chemistry classes and, whatever it is you have you working on. Most of you work jobs, all that kind of stuff. It's just going to move very, very quickly. I highly recommend that you meet with me in office hours or whatever you need to do. If you have questions about the project, make sure that's going forward to be completed. Make sure you're staying up on the homework. And remember, a lot of this material, there just isn't going to be time to talk about in class because, we only meet a couple hours a week and we normally would be meeting, we normally would be meeting 4 hours a week for 18 weeks. We're meeting 2 hours a week for 15 weeks or something like that. So 14 weeks, something like that. So just remember, you got to take lead from the, these lessons that are in here and when those due dates are occurring. So I'll kind of broadly explain some concepts this morning. Some of it I've started explaining before. Some of it I haven't. I would like to remind you that when we have these assignments here in Canvas, this is where you have to turn those things in. Don't email me, right? That makes it literally 50 times harder to keep track of everything and figure out where everything needs to go. You have to submit in here if you want credit. Okay, so make sure you're putting things in the right place. And a couple things coming due soon. You've got correlation stuff was due yesterday. You've got your conclusions due today. I'll talk about that a little bit more so that you know what I'm talking about. And then I think there's another one due soon, isn't there? Didn't I just see one? No, I must be thinking of this one right here that's due. Let's see. This one that's due in a little bit. Oh, and then this one, was due yesterday. So a little late to work on that. So statistical conclusions, what am I talking about here? What I want to see here, just to make this clear for everyone, is you need to start understanding your data. You need to be able to tell me something that takes some time to get into, right? It's sort of a necessity, right? There's this idea in mathematics, they have necessary and sufficient, right? There's things that are necessary, and if you do those, you sort of, they have to be there. But then there's the sufficient, which means, was it good enough, right? Was there enough there? So, of course, you need to, in your problems, in your project, you should introduce your questions and then give us the basic information about the feedback. It's okay to give me the numbers, the mean, the median, the spread, the standard deviation. Anything you think is important and interesting in telling that story should be in there. But that's pretty superficial statistics, right? If that's all you know, then what was the point? Like you can ask yourself, what was the point of asking this question if all I'm going to do is give the mean? Do we really get any kind of underlying understanding or new information that we didn't have before. Your statistical conclusion should be going beyond that. For instance, you may have asked two questions, one about how many hours people work in a week and how many credits they're taking in school. Well, that's great. But do we know a connection between those two? That would be new information, right? That would be things we didn't know before. So you can tell me, well, I asked people how many hours they work, and here's the mean and the median and the standard deviation. And then I asked people how many units they're taking, and here's the mean and the median and the standard deviation. Okay, fine. That's interesting. But it's so much more interesting if you can come out and say, yeah, and we found that by and large, we think that people who work more are also taking fewer units. And here's our here's our scatter plot. Here's our line of regression that shows the clear pattern. You can see the pattern when you look at it, that the more units, the more hours people are working, the less units that they're taking. And we even came up with this linear regression equation, and the R value is 0.85. And so, it not only can we visually see that there's a good correlation here, but our R value supports it. And then we even have this, this would be good. This is when I go, this person knows what they're talking about. And I start thinking this person possibly deserves an A, right? You take the regression line and you interpret it in the way that you interpreted lines in your algebra class. Right? Because if you've got that regression line, if you think about it, the slope in that line is a rate of change. It's a rate of change that relates hours worked to units taken. So you literally can look at it and say, this is why we always, in your algebra classes, when we talk about slope, we'd always throw that term rate of change in there so that people realize, oh, this is actually representing, it's not just how slanted it is on the page. This is, how slanted my line is, it's also giving me something that I can interpret. Depending on what you're graphing, it could be a miles per hour. It could be miles per gallon. It could be dollars per day or dollars per hour or whatever it is you're dealing with. That's your slope right there. So if you take the linear regression that StatCrunch gives you, you can literally make a statement like, well, we see that, and I'm making these numbers up, but we see that for every two additional hours worked per student, they take one less unit or half a unit less or something like that. That, like when I see that grabs my attention and I go, I think this person really learned the material for this course. And of course, I'm not going to give you an A based on one thing, but that catches my attention and I think this person probably deserves an A on this project. Right? Whereas, everyone else is going to, you fall somewhere between an A and an F, right? Somewhere between 100 and 0 is where everyone's grade is going to fall. These statistical conclusions, honestly, that's the reason that you're important. No one's going to care that you can calculate a mean or a median at your job or if you're doing research or whatever, right? We have StatCrunch for that. I don't need you for a median. I don't need you for a mean. And most of the time when people are talking about statistics, I bring up, you hear this all the time. Once you learn some statistics and you start listening to it, you see statistics all the time. You see it on the news. You see it with the politicians. And how often do they talk about mean and median? Occasionally, but not very much. Certainly not standard deviation. What they're talking about is the connections between things. They're trying to convince you there's a connection between this, and we're going to create a new regulation that connects these two and monitors those, and so that we can have better outcomes, right? And then you, as someone who has understood statistics, can think about what they're saying and decide if you agree with them or disagree with them. But it's the statistical conclusions that are usually being discussed. And so that's the interesting part, okay? If all you can do is read numbers that StatCrunch displays to you, then what have you learned? Like, not very much, right? And remember, the whole point of the project is to show me what you've learned. Right, that's what I'm looking for right now. We're not going to publish anybody's project. Right? I'm not going to take that and go, this is so good, let's publish it in a paper because we didn't even collect our data in a way that is scientifically defensible. We did it as a learning exercise, right? But those statistical conclusions really are the whole game. Everything else we're doing was building a base to understand statistics, to see where we're going, but these statistical conclusions are what's important. So when I see someone saying, yes, we see a clear trend that the more hours someone works, the less units they take, and then right? So then I go, okay, I think maybe this person understands what's going on. They've given me a very minimal conclusion, but at least they gave me something. That's better than the person who just read me means and medians and probably won't even get a passing grade on the project. Okay, you gave me some kind of a conclusion. That's good. And now a little bit better would be, well, here's our conclusion, and here's the scatter plot with the regression line and the R value to support that, right? Remember, I've been saying this throughout the semester. You're a lawyer making a case. You've constructed a narrative, and then you have to show evidence that your narrative is the true one, right? That's what a statistician does. You create a narrative, and then you try to convince people with evidence that your narrative is true and accurate. So tell me your conclusion. Well, I think that people who work more, and I might have this completely backwards, so I'm just making up this hypothetical question. It could be that people who work more take more units because they have to make the money in order to pay for their college, right? So this is a hypothetical situation, but I'm giving you examples of what I would like to see so that you can get a good grade on the project and maybe even get an A, right? So, the sort of bottom superficial level would be that your conclusion is something about the more hours people work per week, the less units they take. Okay, that's pretty minimal credit you're going to get for that. If on top of that you show me a scatter plot, you show me the line of regression, you show me the R value, I go, okay, this is better. So that first step, that person, that minimal one, all they did was give me the narrative, no evidence, right? They just say, well, we see some people here. I asked 2 questions, and I kind of think maybe this is the pattern that's going on. But you haven't convinced me. I don't necessarily believe you, right? I could have 2 different groups. One could tell me that students who take lots of units take fewer classes. Students who work lots of hours take fewer classes. And one group that says students who work lots of hours take more classes. Right? And I could be convinced either way. If you just tell me that, all you've done is you've given me the narrative, but with no evidence. All right, that's pretty minimal. That's really, like, in the real world, no one's gonna listen to you if you don't have any evidence, right? So then that next step is you give me the evidence, the scatter plot, the linear regression, the R value. All of a sudden I start to go, okay, this person's going to get a much higher grade than that other paper or that other video that I just watched a minute ago, because this person is actually giving me some evidence to convince me of their idea, right? It's very easy to just sit there with some data and go, I think in my video I'm going to say this. You can just literally make stuff up. But if there's no statistical evidence backing it up, then I don't believe you. And if I don't believe you, then, you're not going to get a very good grade on it. So then you show me some evidence. I go, that's really good, right? And then that, like, A level is where you're going, yeah, and here's our linear regression, and here's my interpretation of the linear regression. Our work shows that, for every 5 hours that a student works, they take 1 unit less in school, or whatever the interpretation of the slope is. I hear that kind of thing, and I see the evidence, and I can see it for myself and see that you did it right. That's A-level stuff right there, okay? So you can see, like, if you just, that minimal conclusion, you're talking about like CD borderline grade. If all you say is, yeah, we think people who take more units, or people who work more hours, they take less units. That's like, maybe a 70 passing, not passing, real dangerous zone. If you drop any at all, you don't pass the class, right? That's like where that kind of level lives. Once you get up to giving me the evidence, you're kind of like in B territory. If you can get up to the A level territory where you're like, you're interpreting the slope of the linear regression and you've given me all that information, then I start thinking this person might deserve an A. Now, that's just for that one piece. I'm not saying the whole project just relies on your one correlation piece. I'm giving you an example of the types of conclusions and interpretations that I want to see. We'll talk more about conclusions. The problem is that 2 of the other major tools that we would use for this kind of stuff, we haven't learned yet. We're about to learn them in the remaining weeks. That is confidence intervals and hypothesis testing, right? So I'm kind of so far talking specifically about the ones we've done. So don't say, well, you said in class that if we did this, we'd get an A. I'm saying for that particular part of your project, I would give you an A grade on that part. If you completely bomb the other parts of the project, then your grade's going to go down, right? But the idea is for each part of your project, you want to do it really good. And if you do A work on each part of the project, then you can walk away with an A, right? That's kind of how it works. So what I want you to do here is start putting your conclusions together. Now, I know you're still new at this, so you're certainly welcome to come talk to me in office hours, and we can look at your data, and you can tell me what you're thinking, and we can talk it out. I have students who do that, and their conclusions usually are a little bit better than their colleagues because they're, their classmates, because they came and talked to me about it. So I would encourage that. Now, here's the thing. Your statistical conclusions, I don't expect to be bulletproof at this point because, like I say, you've really only kind of learned a few of the tools, two of our major tools that you're going to use to back up your conclusions, that you're going to give as evidence for your conclusions, we haven't learned yet, okay? So when you talk about those, you want to, those will help you improve your statistical conclusions. This is really more an exercise to get you thinking about it. Look at your data and start thinking, well, when, again, back to the hypothetical situation, maybe you asked a question about hours worked and you asked a question about units taken. You need to start thinking, well, let's see, does it look like the people who took more units or worked more hours took more units or less units? Or maybe the same. Maybe there's no correlation at all. But you need to start asking that question, okay, so that you can make a conclusion. And I want to be clear here. I feel like sometimes people try to force a conclusion that is a cool statement, right? So in other words, sometimes, and I know I've brought this up in class before, but it seems like a thing that needs to be repeated. It's okay if there is no correlation between your variables. That is a thing that you can report, and then we've just learned something. I feel like sometimes people want to push it to say, yes, these two variables are highly related. Well, don't say that if it's not the case. Only say that if it's true. If you looked at, maybe you asked people their shoe size, and then you also asked people how many units they were taking this semester, well, probably not a big connection between those variables, right? So don't force a connection to exist where one doesn't exist. It is perfectly reasonable to say, well, we thought maybe that the people who were working more hours would be taking less units per semester, but our work shows that's not true. There doesn't seem to be any kind of then you would show your scatter plot and you would show your really poor looking linear regression. You would show me an R value that's close to 0. And you'd say, yeah, we don't think these two variables are related. And here's our evidence why they're not related. And you can see from the graph that it doesn't look like they're related. If you go through all that, I go, okay, this person understands what they did. It just so happens the variables they were trying to connect are in fact not connected. Right? And this happens all the time in statistics. You take two variables you think are not connected, like shark attacks and ice cream consumption. Turns out they are connected. You take two variables that you think are going to be connected, and you go, oh, that's weird. They're not. We do this all the time when we're making decisions at school for the campus, where we're like, I kind of think this is what's going on with students in this situation. If we did it this way, that would probably work good for students. But then when we pull the data and we look at it, we go, oh, it doesn't seem to make any difference whether we do it, option 1 or option 2. It seems like the students have the same outcomes. Sometimes it's counterintuitive, right? So learning that two variables are not related is still an important thing. So don't be afraid to show your variables and say, we thought these were related, but they're not, okay? And you can still do the same thing. That's your narrative, is that two variables are not related. And that, and then you show your evidence for it. So either way, state what you think is going on with the data, show some evidence, and then make a conclusion, right? So here, whatever conclusions you write here probably should not be the final conclusions that go into your project, okay? When I grade these, I'm just looking for basic conclusions, right? I'm not grading them on like, if you get your 10 points here, that doesn't mean you have great conclusions. It means that I'm looking at it and going, okay, they kind of made an effort here. They went through, they did the work. Okay, they're keeping up with the homework. I'll give them their points. But then I'm going to expect it to be a little better in the project because you've had another 3 weeks to sit with it. You've learned about confidence intervals. You've learned about hypothesis tests. I'm saying in the next 4 weeks you will have learned those things, and you can make a better case. You might even change your mind. And here you'll say two variables are related, and by the time we get to the end of the semester, you've changed your mind and said, I don't think they're related. I don't think so anymore. That's fine. You are totally willing to update your information. This is only to get you thinking about it so that you can start thinking now about what variables do we think we might be able to connect, or what variables do we want to show have no difference at all, right? Here's an example of a time when two variables not being related would be really important. Now, again, this is totally hypothetical. I'm making this up. This is just an example, so please don't think that this is real world stuff. I'm making this up. But let's just say some work came out and said that there is no correlation. Again, hypothetical. I'm trying to teach you about the topic here, not about like actual science. But let's just say hypothetically that there was a science that came out that said there does not seem to be a connection between people who get vaccinated and people who get sick from COVID. Well, that is a case where you would have shown that two variables are not related, but that would be really important for our society to know, right? Oh, if I do this thing, it doesn't necessarily mean that I'm not going to get sick over here. Again, hypothetical. I'm not in any way trying to convince you about vaccines. I'm just saying that's an example of a situation where two variables not related would get our attention and we'd go, what? That doesn't seem to match the rest of the science we're doing. What's going on here? And then science would look at that very closely and go, oh, this is a weird outcome. Let's see if we can understand what's going on here in this kind of a situation. So showing that two things are not related can be as important as showing that they are. Now, like the example I gave a little while ago, shoe size and shoe size and credits taken. Yeah, no one's expecting that. No one's going to be that interested if you say, yeah, we thought people with larger shoes were going to take more units, and it turns out they're not. No one's going to be that interested in that, and also it doesn't really seem like a serious question. But you can have times where two variables not being related can be a very interesting conclusion. Okay, so make sure you're doing that. Get your conclusions in there. Try to support it with some evidence. If all so you're just kind of remember those three levels, CBA. If you're just stating a conclusion, you're getting a very minimal grade, right? Maybe in the 70s, maybe in the 60s, depending on how poorly or sparse your conclusions are. You give a conclusion and some evidence, probably depending. Again, it depends, but possibly up in the B range. And then if you do really, really well, that's what kind of gets you into the A range. And it's not like one statistical conclusion. A lot of times people treat this like a checklist. Oh, I made a statistical conclusion. I can check that off the list. You should have numerous statistical conclusions, right? You asked numerous questions. You should have numerous stuff going on. Also, there were other questions remember, you can use any of the questions in the survey. So you might find a question you didn't even ask, and then it ties into what you're doing, and you want to use that. We'll talk about it, right? So that's what I'm looking for in these statistical conclusions. Some people have already submitted that, and we can kind of go forward from there. So make sure you're doing that. Again, don't email me your stuff, okay? If this is where you're supposed to submit it. So if you email me your work, it's not going to get graded because it's been submitted incorrectly, right? So make sure you post it in here. Okay, post it in here so that you can get your points. But sending it to my email inbox or the Canvas inbox is not how you turn these in. Turn them in the correct way, please. Okay. Okay, so where are we then? With that said, this chapter was just due. There was no project part for this. I tried adding it actually in my other class, and I kind of didn't like the outcome. So you can use this in your project. In fact, this is one of those things where if a student had this kind of discussion going in their project and did it well, that would definitely get my attention and go, oh, okay, look what they're talking about. They must really know what this class is about if you're talking about this kind of stuff. But when I made it as an assignment, I think I need to rework my instructions maybe for how I told students to do it. But if you want to talk about binomial probability distribution and you're tying in work that you did somehow, I will notice that in your project. And then we're getting into properties of a normal distribution. So a normal distribution, capital N, normal distribution, remember, is where you have two conditions that need to be satisfied. One is that you're approximately bell-shaped, and one is that you're approximately symmetric. You're never going to get a perfect bell shape because, bells can have different shapes. You can have a tall, narrow bell. You can have a wide bell. So there's a little bit of leeway there, but roughly bell-shaped and symmetric. You're never going to get perfectly symmetric. If you take data that's more than just a few, you ask 10 people, you might get perfectly symmetric data. But if you ask people 1,000, if you ask 1,000 people a question, you ask 1,000 people, how many units are you taking this semester? You are not going to get a perfectly symmetric shape. But, is it roughly symmetric? If I take this half, if this was printed on a paper and I folded it down the middle, would the left half pretty much line up on the right half? If the answer is yes, then, we have an approximately normal graph. If your data is skewed and you fold it over and one side is like really steep and the other side tails off in a long tail, then those two are not symmetric, right? So it really depends on the type of tool that we are using, how closely we care about normality. The good news is the vast majority of statistical tools that we use simply say you have to be roughly normal. Okay, so you look at it, you go, is it symmetric and bell-shaped? Pretty much. Then you probably can use it. There is one tool, and off the top of my head, I forget which one it is. I'll have to talk about it when we get there. There is one tool in our arsenal that is kind of strict about, like, this one needs to be pretty normal in order to apply this tool. But for the most part, we don't have to worry about that. So how can these normal distributions show up? And what if I have a graph that doesn't have a normal distribution? Well, interestingly enough, we can study data that isn't normal, that doesn't have a normal distribution. But if we study the data of the data, then we can come up with a normal distribution. You get kind of meta with it, where you're talking about the summation of the data itself can get into that situation. So, for instance, you could imagine. Let's just say that we took, I don't know, let's go back to the smoking ban. I've talked about this example, but I don't think I've talked about it in terms of Chapter 7 yet in this class. Let's say, a few years ago, the president of the school implemented a tobacco ban on campus, and let's say that each one of you went out into the school and asked students, do you support the tobacco ban? Right? And for the most part, students were supportive of the tobacco ban, sort of mostly overwhelmingly supportive of it, except for even many smokers didn't want there to be tobacco on campus. But, some did, right? We definitely were seeing issues at the end where people were walking around school vaping, which is, I think, why they implemented that. People thought that vaping was different because, it used to always be no smoking on campus, and people were like, well, I'm not smoking, I'm vaping. So they went to a full tobacco ban because people were just not getting the message that, if you're standing in a group of 20 people outside of the classroom and you're blowing a huge cloud of your vape exhaust all around them, it's not really appreciated by your colleagues or your classmates. So they implemented the tobacco ban. Well, let's just say that the true percentage is 80% of people supported a full tobacco ban, which I think is probably about right if I remember correctly. Well, if I send you all out, you're not all going to get 80%, right? So you're all going to come back with a different proportion. One of you is going to get 0.81. One of you is going to get 0.75. One of you is going to get 0.83. And you're all going to have these different proportions. What's interesting is they're going to pile up around, see if I can draw this. They're going to pile up around 80. So if we, let's see, let me switch this over since I don't have the visuals. I was hoping to show you stuff out of the book, but I don't have the book we're using is hard to use for visuals in class. So let's see. Actually, none of you are on Zoom, so that won't do me any good. Let me see. I know what I'll do. Hold on one second. I can do this. Let me look it up on a different page. Here we go. Where's our normal distribution? So here's an example. If you look at each of these, what do we see? We're seeing bell-shaped and symmetric, right? Approximately bell-shaped and symmetric. Here's a graph that comes up a lot, like our typical normal graph. If you have a truly normal distribution, you'll actually know pretty well estimates of the percentage that lie within one standard deviation. So within, let's see if I can get this to come up. It scrolls the wrong part, unfortunately. If I move it up, it's going to snap, I think, to the, oh, here we go, that'll work. Okay, so remember, these are our standard deviations. So in a normal graph, within one standard deviation of the mean, you have about 68% of your data. Within two standard deviations, you've got about, 95 roughly. And within three standard deviations, you get about 98% of your data for a normal distribution, okay? So that's helpful to kind of be able to roughly estimate those values. Yeah, let's go back to where we just were. Let's go back to that one. So let's just say that this, we can do these with, like your typical normal graph is usually made with a mean of 0. Now, you would come back with a proportion of 0.8, around 0.8. So if I sent all of you out and said, ask 100 students if they support a tobacco ban or not, this value right here in the middle would be about 0.8. We might be off a little bit one way or the other, but this would be around 0.8. And then a lot of you would be getting a value here like 0.83, or someone might get 0.75 or 0.77. But your values are going to pile up around here, right? We wouldn't expect a lot of you to come back like over here where you're like, yeah, the proportion I found was 0.3, unless you went to the, where people used to congregate and smoke and asked all of them, then you might get a really low value. But if you did your sampling in the right way, we would expect each of you to come up with something that kind of was in this area. And the further we get away from 0.8, the fewer proportions we would expect to see. So in that case, what happens is as we repeatedly sample, what we would see is it would create a normal distribution. So we're actually creating a normal curve with our collection of data, right? And it would pile up in this manner. So that's kind of interesting that we can go out and measure things, and sometimes the things we measure will create a normal graph. Sometimes we'll measure things where the graph is not normal, but if we repeatedly sample that, our version of the samples, our measurement of the samples will become normal, right? Which is, again, that's where we get kind of meta, like we're sampling our samples and viewing it that way, okay? But that's what that normal distribution looks like. Okay, hold on. Let me catch my place so I can double check. It's hard without the PDF that I was planning to show you. Where am I? Am I on the wrong page? Let me double check something. So going forward, that gives us 23 is. Okay, so let's sort of look ahead at this point. Where we're going soon, we're going, like, the two big things left in this chapter after, I just kind of introduced you to normality a little bit, and hopefully you're a little comfortable with it. The two big things left in this semester are confidence intervals and hypothesis tests. Those are huge. You should be showing me in your project confidence intervals and hypothesis tests. Like, if you don't have one of those, not just that you should do one. For every single thing, like, that's going to be part of your evidence for your statistical conclusions. I should see multiple confidence intervals. I should see multiple hypothesis tests. Okay. Now, what people have a tendency to do is, we calculated the confidence interval. Here's what it was. We calculated a hypothesis test. We got a low p-value, so we rejected the null. Okay. That kind of language right there leads me to believe that you don't even know what any of that means, because students get very good at memorizing those lines that I just said and have no idea what they're talking about. They have that's why we want to see the statistical conclusion. Your conclusions that you get from the confidence interval or from the hypothesis test, that's not the end of the story. That's the beginning of the story. That's the beginning of where you give your evidence and say, therefore we believe that, and then you give me some information there. So what a confidence interval does is it gives you an interval that we believe the true proportion falls inside of. So each of you comes back from asking students on campus if they support a tobacco ban. And one of you says, so I measured 0.82. And one of you says, I measured 0.81. And I measured 0.75. And I measured 0.79. And we get all these values. Some of you would get 0.8. What would happen is we would create this thing called a confidence interval, which is an interval where we say we are fairly confident that the true proportion, it's a proportion we can never really know. If we could, we wouldn't need statistics. We can infer that. That's why it's called inferential statistics. We are inferring the true proportion for the entire population by looking at what we measured for the proportions of our samples. So we can, for that case, we might say we wanted to do a 95% confidence interval. That means we have to be careful with how we give those conclusions, but that's kind of the standard, a 95% confidence interval. Sometimes people use 90% confidence intervals, but then you're going to be wrong a lot more often. Sometimes people use a 99% confidence interval, so you'll be wrong very rarely, but that interval gets bigger. The more confident you are that your true proportion is in the interval, the wider it has to be, right? Because if you think about it, if you shrink that interval, you're increasing the chance that your proportion falls outside of it. If you increase the interval, you're increasing the chances that it's in it, right? Think about the extreme values. If I said, I believe that the true proportion of Ventura College students who support a full tobacco ban is somewhere between 0 and 100. Well, that statement is so broad as to be kind of dumb, because mathematically the percentage of students who support a tobacco ban has to be between 0 and 100, right? So what I just said is mathematically guaranteed to be true, but it's not helpful in any way. Like, who's going to, academic senate, are we going to make a recommendation for the tobacco ban based on the fact that the number of people who support it is somewhere between 0 and 100? No, because that doesn't help us at all, right? So I can make that interval super wide and be guaranteed that I'm right, the proportion's in there, but it's not helpful. So that's one extreme. The other extreme is to pick a point. I think that the true proportion of students who support a full tobacco ban is 0.85473429115. Okay, I'm almost guaranteed to be wrong, but by how much am I wrong? So that's why we create this interval, so that we can say, we ran a 95% confidence interval, and we think that the true proportion of students who support a tobacco ban is between 0.78 and 0.83. That's helpful, because then in Senate we go, oh, it looks like we're talking about roughly 4 out of 5 students. We don't know exactly if it's 0.8 or 0.81 or 0.79, but anywhere in this interval, that proportion being around 0.8 is going to inform us that students overwhelmingly support a tobacco ban. And then we can make a decision based on that. Okay, so that's the idea with these intervals. You're always playing this balancing act between, we want a small interval. We want an answer, like a specific answer. But in real life, if you want an exact answer, it's probably going to be wrong when you're talking about statistics, because we're never going to be able to pinpoint the exact value of a proportion. But we can come up with this interval and say, I think it's inside this interval, right? And that may be helpful to us. A hypothesis test that's a test you run that is a little more strict. It gives you a straight up yes or no answer. It tells you this thing is true or it's false. But there's also a lot more skepticism around hypothesis tests. And like I say, and you should be using them. They should be in your project. I also see a lot of students who memorize by watching the videos and reading the problems they do on the homework. They memorize there's this whole thing you go through of our p-value was very small, so we decided to reject the null, and this was our conclusion. You should go beyond that. If that's all you give me, then I'm going to wonder if you actually understand what you said. And in fact, a lot of people even get that part wrong, where they mess up the part about rejecting the null or failing to reject the null, or one of the cardinal sins of statistics is to say that you accept the null. Never say you accept the null. If you say that in the project, that's one of those bad red flags that comes up. I talked about the other ones that get my attention and go, I think this person really knows what they're talking about. If you say you accept the null hypothesis, that is a big indication to me that you have no idea how hypothesis tests work. So be very careful not to say that. But again, don't lock yourself into just reading what's out of the book and only saying that, because that also indicates to me that you don't know what you're talking about. So, and I know it sounds, I'm not trying to be harsh here. I'm trying to give you all an understanding of what you should be doing in the project if you want to get an A or a passing grade or a failing grade or what it is you want to do. You're always welcome to come to office hours and get some input on those. I plan to do my office hours. The power could be going off any minute, but probably in about 15 minutes it's going to go off here. I'm going to try to do my other class on my office hours from my office today. The Wi-Fi there is very spotty. I don't know if I'm going to be able to do that, but I will try to have those Zoom office hours today on campus so that you can get help if you need. Okay, so feel free to come talk to me about it. The recommendation is that you talk about this stuff first in your groups, and then someone or all of them from your group come and talk to me. I have that where like 2 or 3 or 4 people, or whatever it is, 2 or 3 people will show up from the group at the same time, and they say, here's the conversation we were having about this. What do you think? And then I talk to them about it and say, well, I see what you've got here, and here's how you could make it a little bit better, and here's what you could do here. And then I give them some tips on improving it a little bit. I actually wish more students would do that with the hypothesis testing, because hypothesis tests are one where a lot of students, it's the last thing we learn. It's also fairly complex as far as the logic that goes into it. For some students who aren't used to thinking logically, it's confusing. Some students just pick it up right away, but for some students, the idea of using logic to think about something is sort of a topic they've never done before. And so it can be confusing, and it's the last thing we've done. You don't have a lot of time to sit with it, and all of a sudden you're making your project. It's confusing, but that's when a lot of students get wrong. So feel free to come to my office hours and talk to me about hypothesis testing when we get to that chapter, so that I can help you with that part too. Okay? So I think we'll wrap up there. I should have office hours later today if all goes well, and you can come talk to me about stuff. Otherwise, keep plugging along, keep doing what you can do, and I will see you in a couple days. Okay? And if you're going to try to talk to me now, I would hop in and do it quick, because I'm going to lose power and then pretty quick here. So, and I got to shut down the computer and everything before the power goes out so I don't mess up my equipment. Okay? So, thanks everybody. I will see you in a couple days.